So, in the last lecture, we discussed about different types of about testing transformer. Now we are going to get into a bit more detail about testing transformer as well as the cascaded connection of testing transformer. Means when we have to build more voltage, we will use several transformers together in order to achieve a higher voltage. So that is what we are going to see in this lecture. Okay. So let us discuss about this, the testing transformer. Yeah. So, so this is the construction of testing transformer as such. You can see, the first one is the iron core, where we establish the magnetic flux, and the second one is the primary LV winding. Here, primary LV winding means LV winding means, as you can see here, this is comparative. This is the part which is what this coil as well as the upper coil. These constitute the primary winding. So, what does it mean? That your number of windings in the primary will be lesser, and number of windings then comes the high. What I can say, the secondary winding, like. Then we have the secondary winding where we get our number of turns will be very much larger compared to the LV winding. Then you have the field grading shield as well as field grading shield as well as the ground tank or the base. Here the interesting part is that this ground tank or the base, this is the ground tank or base, it is grounded, right? As you can see here, this is grounded. That grounded tank or the base is grounded. So, and this particular point here, it is at a higher potential. Right. This is at a higher potential and this is downward. So that here there will be a what I can say, there will be a very high potential difference between these 2 points. So in order to avoid a flashover, we have our high voltage bushing here. Understood? High voltage bushing and our high voltage electrode with this corona sheet. This is to avoid the flashover that can happen between the high voltage electrode and this grounded tank or the base. So that is the construction of a testing transformer. Okay. Main point here is that LV winding is having lesser number of turns, and you have a high voltage winding which is having very much more number of turns. Okay, the construction also you can see. Okay, it's a cross section, so you can imagine it is it is similar to like what I can say, cylindrical construction of this windings. So now, in the before we have already discussed that we have to linearize. So when you take the potential distribution as such, but we get a curve like this. But a better one is what whenever a potential distribution is linearized, like this curve here, then we say that yeah, then it is better. So, but on the normal construction, we will have a curve like this, where most of the potential is nearby your high voltage electrode, right? And there is lesser potential distribution towards your low voltage electrode, nearby low voltage part. So that's a problem. Because of that, more stress will be on the winding insulation. So we have to avoid that. That process is what we call as what that process is what we call as uh, linearization. Okay, that process is what we call as linearization of potential distribution. So now let us see that how to linearize. Okay, there are three ways. One is by use of trapezoidal windings. Then we can try with the use of static sheet, and the third one is use of interleaved winding. Understood? So the first A and C is about how you are winding your high voltage winding, and the second one the thing is about what the use of a static sheet. Okay? We will see one after another in order to understand. So the use of trapezoidal windings. Okay, let us see how it helps in linearizing the in linearization of our potential distribution. Okay, so if you I think you will remember about the series capacitance. Series capacitance is formed by what? It is formed by that is the interlay capacitance, right? Formed by the conductors on both sides as electrodes and insulation as the dielectric, right? Like in between, you have the conductor, and in between you have your insulation, right? That is how the series capacitance is forming. Parallel capacitance was formed how? Parallel capacitance was formed between the between the LV and SV, or between the LV and between the winding and the core, right? But this is the series capacitance, and it is formed by the conductor, like in the winding between each conductor you have an insulation, right? So that is what is making this series capacitance. And capacitance is given by what? Capacitance is given by epsilon 0, epsilon r, A by D. Right. And this, when considering this winding, this distance between the windings, or distance between the plates, right, that remains same, as well as the permittivity also remains. But interestingly, when as you have seen in the construction in the first slide, you have already seen that the iron core, it is having a construction like this. Like the construction of the LV winding is in such a way that as you move from inside to outside, what will happen? Your area of cross section is changing. Right. So that is what is of importance here, and area reduces towards the outer layers. So there is a difference in the there is a difference in the series capacitance arising due to this reason. That's a problem, right? So there is a difference in the CS arises due to this reason. As you move away from your move away from towards the outer layers in the winding. So what can we do? So the construction is quite like this. As you can see, as I said, it is like what? It's like a cylindrical construction like this. So the distance from the center to this, that is R1. From here to it is R2 up to Rn, right? So this is how this is the cylindrical surface, and between each of them you have the same distance. Between each of these windings, you have a distance called d. Right. So between each winding, your distance is d, and the winding, as we can see, the cylinder shape will change, and the R1, R2, Rn of that will change. Right. So with that, your area also will change. So but if at all our series capacitance are all equal, then we have a more, what I can say, a more linear distribution of the potential. But now the series capacitance is not going to be equal. The trapezoidal windings, they are a special type of helical windings, and by winding it, what we are achieving is this. This is the expression for capacitance. So if we take the first winding, what will be the capacitor? Epsilon A divided by D. So here, since it's a cylindrical surface, the area, surface area is given by what? 2 pi r1 is the perimeter, and into what? Into the length L1. Right, L1 is the length of this conductor. So 2 pi R1 L1 will give us what? It will give us the cylindrical surface area, right? So epsilon into 2 pi R1 L1 by D will give you capacitance. For the second winding, it will be epsilon into 2 pi R2 L2 by D. Like that, we can write up to the nth winding, right? At a distance of Rn. So this way, uh, by winding it in a trapezoidal winding, which is a special kind of helical winding, what we are achieving is this only. We equate all the capacitances, series capacitances, so that our potential distribution is more uniform. So epsilon into 2 pi R1 L1 divided by D equal epsilon 2 pi R2 L2 divided by R2 epsilon into 2 pi Rn Ln divided by D. In this, as I already said, epsilon and D are constant. So what we are equating is what we are equating. We are equating, and we can cut off 2 pi all around this equation. So what we are really doing is this only. R1 L1 equal to R2 L2 equal to Rn Ln. This condition is satisfied in our trapezoidal winding, so that what will happen? Our potential distribution will become less non-uniform with the trapezoidal winding. I think it is clear. Now let us move on to the second type of arrangement, which is called as the static shield. In a static shield, as we already discussed that, I think you remember the coefficient alpha, right? So as alpha decreases, the potential distribution will become more uniform, right? As alpha decreases, the potential distribution will become more uniform. So in this thing, what we are doing is, this is the this is the I can let me say the winding diagram. This CSA, CSV, CSC, if you avoid it, without that, what it will be like this part of it, CSCG, that is the equivalent circuit of what our normal winding, right? So series as well as parallel combination is there. So uh, this CG by CS, it can be decreased by how, by increasing the CS, right? If we increase the CS value here, as the CS value is increasing, then your alpha will come down, right? So in order to achieve that, we have to increase the CS. So to increase CS, we are making a constructional change in our winding. So this is the high voltage end, as you can see, and this is the grounded part. So CS is like this in series. As we know, when in the potential distribution, if you remember the potential distribution curve, most of the voltage is getting where it is on the high voltage side, right? So the stress is more on the high voltage side. So on the high voltage side, you take a copper sheet and is covered over the winding, and connection is made with the high voltage terminal. Means you are just taking a copper sheet, a copper cover over the winding. Understood? So the addition of this thing, it will add this copper sheet has one terminal and your winding part has the another terminal. So that will add parallel capacitance like CSA, CSB, and CSC on what, not on the complete section, but on some part of the winding which is near the high voltage end. So that what will happen, so that your the capacitance, this will come in parallel like this. So the capacitance CS values on this part, that will become parallel and it will start reducing. Understood? So it will increase since they are in parallel. So they will increase. So CSA, CSP, CSC comes in parallel with CS, thereby what, reducing the effective CS. Understood? That is what is done here. Now, this helps in making the potential distribution more linear. Clear? That is that is what is done here. One thing I did is that this is not reducing, but it will increase. Since there are capacitances in parallel, it will increase. So this is wrong. So ultimately, we increase the CS so that our alpha will come down, and we have a more linear distribution of potential. So that is how what we do with the static shield. Now, another way is to use the use of the interleaved winding. Okay. Now, the inside part is the our winding part. Like we divide the winding into 10 equal sections. 1, 2, 3, 4, 5. It is for an example. Okay. 1, 2, 3, 4, 5, 6 up to 10. For each winding, you can say. So, and if we see the equivalent circuit, as we can see, which is on the top, drawn like this, we can take what the series capacitance is referred as C like that. So, for all the 10 sections, between each winding, what you have, like which between each coil you have a capacitance between your insulation, so that is constituted by this C part. So first, let us say first on the first terminal we have V volt, then on the by the second terminal what we will have 2 V volts, right? Like that 3 V 4 V, like that we will get the 10 V volts by the end of this winding. That is what is meant by this is a continuous connection, right? The windings are connected one after another in series. So it's a quite normal connection. So all our 9 capacitances are how they are connected in series, right? All 9 capacitances are connected in series. So our equivalent capacitance, that will become what, C by 9. As you know, when it comes series connection, series combination of capacitors, then it is like it is quite opposite to what we do with resistance, right? So EQ equal to what? EQ is given by C by 9. It will become 1 by 9th of the one capacitance value. Okay, keep that in mind. And now we will get into, this is a continuous connection and this is not interleaved winding. Now we will see what is meant by interleaved winding. As the name suggests, what, you will leave one winding, get to the other. That way is what interleaved. So an interleaved connection is shown here. Here we have two sets of winding. Okay, what we have two sets of winding. One is called as set one, and another one is what, the set two, as is marked here. So this is one set. This is what, the second set. Okay, so they are what they are put nearby each other. So from, as you can see, from the first winding, your connection is coming like this, and it is not getting into two, as as was the case when we were taking continuous winding. But where it is going to the third winding. From three, it is going to the fifth winding. From 5 it is going to the seventh winding. From 7 it is going to the ninth winding. Understood? So and from 9 what 9 it is going to the second winding. You got that. You got my point. So that is how it is done. But so there comes a difference also. So here we have a voltage V, but on the second winding, what we have on the second winding, you have a voltage of 6 volt because it is coming after this. This V, here it is 2V, here it is 3V, here it is 4V, here it is 5V, here it is 6V. Understood? Means here V is reduced. Here what? Since the conduction was here, here it is 2V. Here it is 3V. Right. Like that, we have two groups, and because of that, between each of them, we have how much is what is the potential? Here, if we have V, here we have 6V here, and here we have 2V. Here we have 7V. Like this, that is the change we have here. So in group one, I have a potential difference of I have a potential difference of 5 volt, right, in group one with the 5 capacitors, and in the group two, what we have total there are 9, right? When you have 10 windings between them, you have 9 capacitors. So group two have a potential difference of 4 volt across each of them, right? You see here, this is the V volt and this is 6 volt. So what is the difference? It is 5 volt is the difference between them. This is 6V and this is 2V. So that between this one we have what is the potential? Potential is 4V. Like that you can see the all around. Then you will find that there are 5 capacitances where you have a potential difference of 5 volt, and there are 4 capacitances where you have a potential difference of 4 volts. So that is the major difference here. There are the two groups, group 1 and 2. Now, the total potential difference between the complete turns means turn 1 to turn 10. That is how much? That is 9 volt, right? Whether it is the continuous or the this winding, that is going to be 9 volt. So now it is about capacitance calculation, and for that, let us take the energy here. What is the energy associated with the capacitor? It is given by half CV square. So you can see it quite clearly. For the first group, you have what 5V voltage, and there were 5 capacitances. Right. So we took half CV square, half C into 5V all square into what? Into 5. For what? For 5 capacitance. And for the other 4, we have 4V voltage across them, and there are 4 capacitances. So we took what? Half C into 4V all square into 4. So that is the energy. So totally, the how much it will come? 5 square is 25. 25 into 5 is 125. 4 square is how much? 16. 16 into 4 you can do. So total it is how much? It is 189 here. So half into 189 into CV square is what you will get. That is about energy. Now if you take the equivalent capacitance, okay, if this now this is an interleaved capacitance, right? So in order to calculate the equivalent capacitances, let us say it is equivalent to what? Connecting a capacitance got equivalent capacitances across how much voltage? 9 V, right? Because it is from V to 10 volt. So 9 voltage is 9 V is the total potential difference. So half C equal to 9 V all square. That should be equal to whatever we calculated just now, half into 189 to CV square, right? Then we can find out this CEQ2 here. Means what? CEQ1 was what for the continuous winding. This is a CEQ2. So for the interleaved winding, you will find if you equate this part, this V square will go, and you will find in terms of C what you will get. You will see that CEQ2 is given by 7 by 3 C. Understood? You can do that yourself. So it is this 9 square is 81. It will come to this side, and you can cut it down with 189, and you will get the equivalent capacitance of the interleaved winding is equal to 7 by third of the capacitance values. Now, comparing it without the interleaved winding, what we will find? So, for the without the interleaved winding, the CEQ1 was given by what? 1 by ninth of the capacitance, and with the equivalent capacitance, it is given by 7 by third of the capacitance value C. So with that, we will find that our capacitances, the total equivalent capacitance with the interleaved winding is given by 21 times the equivalent capacitance without interleaved winding or with a continuous winding. So with that, we are increasing the series capacitance. So what will happen again? You will have what CS increases with the use of the interleaved winding, and thus you have a potential distribution becomes more uniform, right? So that is quite obvious as we have seen in the static sheet winding. So that is these are the three ways of improving your distribution of potential. Now let us get into the cascade connection of testing transformer. So it is quite easier. So the main advantages is this advantages when we are talking about higher voltages above 500 kV. And what we do is this only. If we cannot use a single unit because of the constructional problems, so like you cannot have that much insulation on this thing. So what we will do, we will subdivide in several groups and we will connect them in cascade. Understood? So that we in series we will have a higher voltage at our output. So that is what we do with the cascade connection. Then another point is that once we have this cascade connection, then otherwise the size of the transformer will be so huge. So transport and erection will become much easier when you have a cascade connection of transformer. And a main prerequisite for this cascade connection is the existence of a tertiary winding. This we have already seen in another connection. So just similar to this, right? Just similar to that, here also we should have a tertiary winding in each testing transformer so that we can make it cascade. Okay. I think now itself you got an idea about the work. Let us get into work. It is like this. As shown here, you have a first stage, then you are what you have, then you have a second stage, and then you have a third stage. On the first stage, you apply a voltage V1, and you get a what? It's a normal high voltage transformer, one single testing transformer. So that you apply low voltage, you get what? You get higher voltage. On the same iron core, you have a tertiary winding as shown here. This is your tertiary winding here. On the same iron core, you have a tertiary winding. So with the tertiary winding, you are able to take the potential V2, potential V1 to the next set of testing transformer. Understood? So this V1 will again produce a voltage V2, V2 here on this side, and you have a tertiary on the second stage also. So with that, it is you are able to take the voltage to V2 on the third stage also. Now on the first stage, you have a potential of V2, and afterwards you are giving some insulation here but in order to so that since your grounded tank on the second stage is here, it should be able to withstand it. So for that you give enough insulation. Now on the second level, you will have an added potential of how much? This will be 2V2 up to here on the second level. On the third level, again adding V2 more, you will have what? Higher voltage here. Understood? Like I have a transformer of 200 kV, 230 by 200 kV. Okay, so here I apply normal single phase voltage and I will get here 200 kV. Adding the second level, I will get 400 kV. Adding a third stage, I will get what? 600 kV. Okay. It is not that easy as it looks. Okay, let us see the main concerns. So there are three stages consisting of transformer with the same voltage ratio as you can see. The first stage is also V1 is to V2. Second stage also is V1 is to V2. The third stage also is what V1 is to V2. Okay, even we are that is how we make this thing. Only difference is that what we have a tertiary winding. That also is quite similar. That just takes the same potential V1 to the next level of the testing transformer. Now, stage 1 and stage 2 are having a tertiary winding, as you can see. Stage 3, we are directly getting it out. So, that does not need any tertiary winding. So, each stage is designed to withstand the design potential difference. That is the meaning, as I said earlier, about this insulation shown here. Understood? So, that is the meaning of this insulation shown here as well as here in order to withstand what that potential, high potential difference. Now, let us get into that. I think you got an idea about the operation as well. Now, let us get into the kVA grading. That is more important. Like how much kVA it is giving. Okay. So overall, on this side, you have a potential of what? How much? 3V2. And let us say the rated current is I. So our load kVA is how much? The kVA load is 3V2 into I. Right, it is quite easier. So 3 times V2 into I is the total load, kVA load here. Right. So, but now let us see. If we take the stage 3, V2 is the potential, V2 is the potential, and I is the current. So, total kVA rating, let us call it as P, and how much it will be? The kVA rating will be V equal to V2 into I. So that will be the total potential. That will be the total kVA rating in the secondary of the stage 3. Understood? In the stage 3 secondary kVA is given by V2 into I. And so in order to give the, if this is V2 into I, transformer does what? It is power transfer. So whatever be the power here, that should be supplied by the supplied by whom? supplied by the it will be the primary kV of the stage 3. Understood? So primary kV of the stage 3 will be P only. The same should be supplied by whom? Now we come to stage 2, because this part is what, this is a tertiary winding of the stage 2. So there what the same power will be, what the tertiary kV also will be how much? The tertiary kVA also will be given by P. Tertiary kVA also will be given by P as shown here. Understood? So that is one interesting part here. Now the tertiary kVA is P. Who is supplying that? That is supplied by the stage 1. And apart from that, this is having a kVA of how much? V2 into I means again P only on its secondary side. So here it comes what? In the second stage 2, you have a kVA grading of V2 into I or P here, and from the tertiary also you have a P. So totally how much, what will be the kVA rating? It will be 2P, right? So the primary, that is the secondary kVA is P to AP. The primary should supply that much power, or that is given by what? P plus P equal to 2P. That much kVA needs to be supplied by the by the stage 1. Sorry, the primary of what? The primary of the second stage, or the same should be supplied by whom? The stage 1 tertiary also. So what we discussed is that what yeah, yeah, now it's fine. Now uh, so here we have a 2P power, 2P kVA needed, and the same should be supplied by whom? It should be supplied by the stage 1 of the first stage. Sorry, the tertiary winding of the first stage transformer. So along with this 2P, since it have to supply V2 voltage here, when with the current rating of I, you again have what? V2 into I, or the P on the secondary of this one. Tertiary kVA is 2P, because that needs to be supplied to whom? For the second stage. And with the along with the 2P, you have to supply how much? P more, or the V2 into I more. So the total primary kp is given by how much? 2P plus P equal to 3P, right? The 3P, right? Now the total installed kVA, this is the primary kVA of this one alone. If we take the total installed capacity, this primary itself alone is supplying how much? 3P. Understood? The primary alone is taking 3P. Clear? Primary alone is taking 3P here, and the secondary alone, the secondary winding alone, secondary testing as some alone is taking 2P. Third one alone is taking P. So totally how much we will get? 3P plus 2P plus P equal to 6P. That is the total installed capacity. Okay. So for transferring how much power? At last we are only getting V2, what, 3 V2 into I, right? 3 V2 into I. Oh, that is 3 V2 into I means that is 3P kVA. P means V2 into I. So in order to transfer 3P, we have to install a testing transformer set of how much? Of 6P. So the utilization factor, the utilization install capacity, it is called utilization install capacity, is given by what? Whatever is used, that is 3P. Whatever is installed, that is 6P. 3P by 6P means we are only utilizing 50% of the installed capacity on what? On rated working also. On whenever it is working on like V2 and 3 V2 and with I current, we are only utilizing the 50% of the installed capacity. That is the main problem here, and that is what we meant by this KVA grading also. So in reality, how a testing transformer is looking is like this. So not this whole arrangement. This is our cascade testing transformer arrangement. Understood? So each of them are connected testing transformers like this. So they are connected in cascade form, and this is basically a rectifier thing to take a just like something 1200 kV or something. So that is used for that, and then this is another one. Here the difference is that this is the this kind of construction is what we have discussed till now, and there is another construction where you have a construction of core is quite like this, quite simple. So both we can use. So this is another kind of testing transformer in reality. Okay. So this is about testing transformers. These are used widely for different purposes, mainly cascade connection, so that we can take higher voltages without making the construction more complex or design more complex, we can just cascade it. Several testing transformers together in order to achieve whatever higher voltage we are looking for. Okay. So with this, testing transformer part is over. Next lecture will be on series resonance circuit, another way of high voltage AC generation. Thank you. So see you in the next lecture. Thank you.